Hey guys, my name's Ethan Taylor, and today we're going to talk about constructive and destructive interference. I hope my illustrations help and that I'm clear enough. So right here we're going to start off with just a basic illustration of what a wave is. We've gone over this a couple of times, so I'm sure you guys know what this means, but just bear with me. Here we have a peak at the top, a trough at the bottom. We have a equilibrium point, which is exactly halfway in between those two. And we have a wavelength, that is the distance measured from peak to peak or trough to trough. And the amplitude, which is right there, is actually the distance from the equilibrium point to the peak. Again, amplitude is equilibrium point to the peak. Awesome. So interference is right here anytime we have two waves that come in contact with each other. So we get a couple different patterns when this happens. We get constructive and destructive. And we'll start with constructive. This is when a peak meets a peak and a trough meets a trough, also known as in phase. So right here, this blue wave and purple wave, known as Y1 and Y2, if we were to bring those two together and they were laid on top of each other correctly, just like that, right there, we would get an additional property between the two, where the 1 meter and 1 meter amplitude of the two waves, again, 1 meter here and 1 meter there, we would get a 2 meter amplitude wave over here. And that's expressed here with this equation, y total, which is the orange wave, equals y1 plus y2. Now for this to happen, we do not have to have equivalent amplitudes. If this wave amplitude was 3 and this wave amplitude was 5, we would end up with an 8 meter amplitude wave. So that's constructive interference. Destructive interference is when a peak meets a trough and a trough meets a peak. And that's basically, to kind of sum that up, it's an out-of-phase wave. So we're going to use a definition that kind of helps understand this. It's called pi-shifted. A pi-shifted wave, so we have y1 and y2 here. A pi-shifted wave, down here it says this can also be characterized as a wave identical to wave 1. So we've got y1 and y2, they're identical. But y2 is inverted 180 degrees. So it's actually symmetrical, but just inverted. So in other words, it's not identical. It's pi-shifted. Pi-shifted can also be when you have equal distances from the detector. So over here we'll say this is the detector, say we're hearing a noise, this is where our ear would be, and over here is the source, this is where the speakers would be. So if both sources for y1 and y2 are at equal distances to our ear that's hearing the music, and we take the two waves and they have destructive interference properties, in other words they subtract from each other, we know these are pi-shifted waves to each other. Now again, this is a 1 meter wave, and this is a 1 meter wave. So when we have destructive interference, and we said that it was a subtracting property, and we see that it kind of overlaps trough to peak and peak to trough. When those overlap, we get a subtraction of the wave. Because these two amplitudes are the same, we actually get no wave at all after. And this is known as complete destructive interference. So we'll kind of go over why this is important, why constructive and destructive interference are important, and kind of an application for both. But for destructive interference, here's an equation: y total equals y1 minus y2, and the absolute value, because you're never going to get a negative wave. So up here we had the example of the source, or the two speakers, being equal distance from the detector. Now what happens if we take those two sources, or one of the source, and we move it so it's not equal distance from the detector? And that's what this section right here says, is calculating. We're going to calculate between constructive and destructive interference when the source distance changes from the detector. So first, we know what a pi-shifted wave is. We understood that. We went over it here. But I want to go over what an identical wave is. An identical wave is basically when you have source equal distance. So source equal distance. Again, the two speakers are equal distance from the ear. So when the two sources are equal distance from each other, or sorry, not from each other, but when the two sources are equal distance from the detector or the ear, and they come together and they're constructive, these are identical waves. Now, in order for them to be identical, they do not have to have the same amplitudes. In other words, this could be a 2 meter and this could be a 4 meter. Now, to kind of calculate what's going to happen with the constructive and destructive interference when the wave source changes distance from the detector, what we're going to do is use this equation up here. And really these two are the same equation. This one we're going to use for identical waves, and this one we're going to use for pi shifted waves. And again, they're the same equation. I just wrote, I color coordinated which one's going to be pi shifted and which one's going to be identical. Purple identical to blue, which is right here. Purple is identical to blue. Blue is pi shifted to green. So x right here, delta x or x, what x is, we'll just say x1 and x2. x1 and x2, what they are is they're the distance of the source from the detector for each wave. So x1 is the distance of this speaker from this source, and x2 is going to be the distance from, there we go. And x2 is going to be the distance of the blue source to this detector. So again, x is the distance of the wave has to travel to get to the detector. So if we were to take this purple wave and we were to match it up, it's identical, and if we were to shift it just half a wavelength, we see that this is destructive interference. If we shifted another half wavelength, so that's a full wavelength from where it started, this is constructive interference. Okay, so we can see right here, if waves are identical, we get constructive interference anytime the change in x is a full integer, 0, 1, 2, etc. We get destructive interference anytime the change in x is a half of a wavelength. So that's kind of a rule of thumb for identical waves. Now, we'll see what happens. What's the pattern with this pi shifted wave? We have destructive interference, move it half a wavelength, and we get constructive interference. And we move another half wavelength, we get destructive interference again. So I'm sure you guys have guessed it. The pi shifted waves, so down here, when we have constructive interference, change in x is actually going to be swapped from that of identical. It's going to have half a wavelength. It's going to equal half a wavelength. The destructive is going to be a full integer. And again, when I say change in x, and we say a half wavelength or full wavelength, we know a wavelength is going to be this distance to this distance, or sorry, this point to this point. And if we were to measure those, we would get a specific number. We'll say in this case it's 4. If these two waves, if this green wave and this blue wave, which are pi shifted to each other, if we were to move this just half a wavelength, so 2 meters, we'd get constructive. If we moved it another half wavelength, so that's another 2 meters, we get destructive interference. In other words, a full 4 meters with pi shifted waves gives us destructive interference, which is what this is stating down here. So now to kind of get into the applications of this, when we have two speakers that are identical to each other, and speakers are a really good example of this phenomena, but when we have two identical speakers, so when you have multiple speakers within your home stereo, in your movie theater, you name it, we get constructive interference with them, we end up getting a louder sound, which makes sense. When we have this other wavelength and we get destructive interference, this is actually an application we can apply to noise canceling, which I thought was kind of a cool application. So to kind of illustrate this, I drew this headset down here, and what we have is we have a ambient noise. So say you're studying and you hear some people in the snack zone that are really talking loud. This noise, if you had noise canceling headphones on, what's going to happen is this ambient noise starts coming through the actual headphone. It comes through the headphone into this microphone. The headset actually will then allow that same ambient noise to come through, which is why this other small blue wavelength is coming through. So it basically goes all the way through. But in addition, the headset will actually mimic that noise, but offset it so that it's a destructive interference, giving noise canceling. It's kind of a really cool application, but for whoever made noise canceling headphones, it's pretty intuitive if you can understand the difference between destructive and constructive interference and how to apply those electronically. But anyways, again, cool application. Noise comes into the microphone. The microphone allows noise to go all the way through into your ear, but with addition to that noise, we have a new wave that the headset sends through that's going to cause destructive interference. So again, I hope this video has kind of helped you understand the difference between constructive and destructive interference. It's been a fun semester. I hope you guys have a great summer and you stay safe and healthy. So thanks again.